औज़ुबिल्लाहि मिनश्शैतानिर्रजीम बिस्मिल्लाहिर्रहमानिर्रहीम। आज हम एक प्रॉब्लम करने वाले हैं, एक एग्जांपल करने वाले हैं उस आइडियल वेपर कंप्रेशन रेफ्रिजरेशन साइकिल के बेस पे जो हम पिछली लेक्चर में देख चुके हैं। हमारे पास जो स्टेटमेंट है वो सामने पड़ी हुई है, वो है कि रेफ्रिजरेंट 134A is the working fluid in an ideal compression refrigeration cycle. The refrigerant leaves the evaporator at minus 20 degrees Celsius and has a condenser pressure of 0.9 megapascal. The mass flow rate is 3 kg per minute. Find COP, coefficient of performance for the refrigeration, and COP of the Carnot cycle. Of the refrigeration, basically we reverse Carnot cycle for the same T max and T minimum and the tons of refrigeration. So we have to find out three things: COP for the refrigeration for this particular ideal vapor compression refrigeration cycle, and then for the COP of the reverse Carnot cycle, and then the tons of the refrigeration. Now what is given in this whole statement? So we are actually going to see the given data or knowns. So first it was refrigerant. We know that the refrigerant is 134A. It is given that the refrigerant is 134A. Second thing, it is an ideal vapor compression refrigeration cycle. So it is an ideal. So whatever we are going to do would be ideal, would have no losses incorporated. Third, exit temperature of refrigerant at evaporator, which is given as minus 20 degrees Celsius. Condensation pressure is 0.9 megapascal and the mass flow rate is 3 kg per minute. So these are the 5 things which we know. Now to further pursue this problem, we have to draw the schematic as well as the TS diagram for this problem, and then it would be easy for us to understand what is given and what is required. So this is the schematic and the TS diagram for this problem, and we already have discussed this schematic as well as this TS diagram in the previous lecture. Now from 1 to 2 the process of compression takes place, and here on a TS diagram this is 1 and the compression takes place from 1 to 2. This is 2. Now you can see that from 1 to 2 the compression process takes place, due to which the temperature rises, though the isentropic compression, because S1 is equal to S2. So whatever is the entropy at 1 would be the entropy at 2. Then from 2 to 3 we have condensation process, in which the superheated vapor is converted into a saturated liquid, and this is 3. So from 2 to 3 the process of condensation takes place, which means that the heat is rejected. QR, heat is rejected. Now from 3 to 4 what is happening, that we have an expansion valve, and we know that the expansion is not isentropic. In the expansion valve it is a throttling process, and in which the enthalpy is constant. So from 3 to 4 there is an increase in entropy. So now here S3 would be different than S4. Now you can see that this is S3 and here is S4. So S3 is different than S4. The entropy has been increased in the expansion process, and this is 4, state 4. Then from 4 to 1 there is an evaporation, and the heat is actually absorbed by the refrigerant from 4 to 1, and it is QA, or Q absorbed by the refrigerant. Now remember, these two lines this line and this line are the constant pressure line. So whatever is the pressure on this line would remain the same throughout this line, and whatever is the pressure over here would remain same throughout this line. Now there is a very effective method of solving these kind of problems, to draw a table. When you draw a table, so what happens that you know how your problem is going to pursue, what are the knowns and what are the unknowns. So for that, this is very important table. So you have to draw this table in which there are certain things. Number one, node, then the temperature in degree Celsius, pressure in kilopascal, fluid phase, in which phase the fluid is at a particular node or a state. Then we have enthalpy, whose unit is kilojoule per kilogram. Then we have entropy, again kilojoule per kilogram Kelvin, and mass flow rate, which is kilogram per minute. And you can see that since it is an ideal process, the steady flow, so throughout the mass flow rate is assumed to be same, 3, 3, 3 and 3. Now whatever is written right now in this table are the knowns. Since what is node 1? Node 1 is right over here, which is the exit of our evaporator, and we know that the exit temperature of the evaporator given is minus 20 degrees Celsius. So I have written minus 20 degrees Celsius. Now what is the state over here? As you can see, it is on a saturated vapor line. So it is a saturated vapor. So the fluid phase is saturated vapor. At 2.2, after compression over here, we do not know the temperature, but we do know the pressure, because it is given that from 2 to 3 the condensation pressure is, whatever is the pressure at 2 would be the pressure at 3, because this is a isobaric curve, as you can see, from 2 to 3. So whatever is the pressure at 2 would be the pressure at 3, and which is known, which is 0.9 megapascal, or since it is kilopascal, so it is 900 kilopascal. And whatever is the pressure at 2 would be the pressure at 3. So whatever is the pressure at 2 would be the pressure at 3. Now at 2, you can see that the vapor is in a superheated range. In a superheated vapor, you can see that it is above this vapor, saturated vapor line, and it is outside. So it is the superheated steam and superheated vapor, basically, not steam. We are actually using the refrigerant 134A. So at 2 we have a superheated vapor. At 3 you can see it is lying on a saturated liquid line. So we have a saturated liquid. Similarly, at 4 you can see at 4 there is the same temperature what is at 1. As you can see, this is the same temperature line. Whatever is the temperature T1 is equal to T4. So whatever is the temperature at 1 would be the temperature at 4. T1 is equal to T4, and that is why whatever is the temperature at 1 would be the temperature at 4, and the state is liquid vapor mixture. Now this is that state which need a lot of attention, because all these are pretty easy to solve, but this needs a lot of attention, and I am going to solve this for you as well. Now at 4 the process is not, from 3 to 4 the process is not isentropic, but it is isenthalpic. The enthalpy is same. We have already discussed it. Now we are going to find out the remaining unknowns which are right in this table. The empty spaces are the unknowns, and we are going to find out all these. First, we have at node 1, what is happening, that there is an evaporator exit, or you can see that there is an inlet to the compressor. Either you can say exit of a evaporator 1, or you can say inlet to the compressor. Now at 1, so it is minus 20 and it is saturated vapor. Since it is saturated vapor, it is lying on a saturated vapor line, so we are going to use these tables. You can see that it is table saturated refrigerant 134A. Now this table is actually particularly for 134A. It cannot be used for any other refrigerant. It is for the refrigerant 134A. Similarly, you will find out different tables for different refrigerants. Now, as you can see that at temperature minus 20 degrees Celsius, the enthalpy, the saturated vapor enthalpy is 235.31. So I am going to write this, that, and the pressure over here is actually 132.9. From table you can see that the pressure is 132.9 kilopascal. The enthalpy is 235.31 kilojoule per kilogram, and the entropy is 0.9332, and the entropy is 0.9332. You can actually see it right over here. It's 0.9332, and the enthalpy is right over here. But remember, you are going to see the saturated vapor entropy and the saturated vapor enthalpy because we are in a vapor. As you can see over here, we are in a saturated vapor state. Then it is very important to know that whatever is the entropy at 1 is the entropy at 2, because it is an isentropic compression. So whatever is the entropy here at 1 would be the entropy at 2, and it is 0.9332. So again, you can see that we have a pressure now. We know pressure, we know the state, which is superheated vapor, and then we know the entropy. So now what we are going to use, we are not going to use the saturated refrigerant table. This was the saturated refrigerant table. Now we are going to use the superheated vapor table, because this state 2 is in a superheated state. It is a superheated state. So, and the pressure is actually 0.9 megapascal or 900 kilopascal, which is actually right over here. You can see it is a superheated refrigerant 134A. It is superheated refrigerant 134A, and this is basically that 0.9 megapascal. Now you can see that at 0.9 megapascal, what we know the entropy, and this is the entropy, and the entropy is 0.9332. So 0.9332 will come right over here between this and this. So 0.9332 is this in entropy. Now what we are going to do, we are going to perform interpolation, and after interpolation we will get to know that the temperature would be between 40 and 50, and that comes out to be basically 44.74. It is basically 44.74. 44.7 and the enthalpy would come out to be 275.1. So now you can see that we have found out with the help of the known pressure and the entropy, which was same as that of S1. Now in third stage, what is here, that the condensation has been done and the refrigerant has been converted into saturated liquid. So over here now you can see that again we know the 900 kilopascal pressure, we know the state. Now whatever is the pressure at 2 would be the pressure at 3. So I have written that whatever is the pressure at 2 would be the pressure at 3. Now what is the temperature at 3, or what is the enthalpy and the entropy at 3? So we are going to use the saturated table again, saturated refrigerant table again, and now you can see that at 900 kilopascal, so at 900 kilopascal we have basically right over here. The saturation temperature, as you can see, that it is 0.9 megapascal over here. So 0.9 megapascal, the saturated temperature is 35.53. 35.53 is the temperature. 35.53 is the temperature over here. As you can see, this temperature is less than what is the temperature at 2, because at 2 it is at higher temperature and at 3 it is at lower temperature. So it is lower than the T2 temperature. Then the saturated liquid enthalpy right over here would be basically 99.56 kilojoule per Kelvin per kilogram. This is 99.56, and the entropy would be basically 0.3656, is 0.3656. Now earlier we used that whatever is the entropy at 1 would be the entropy at 2, but here, since we know that the entropy has changed, so we cannot say that whatever is the entropy at 3 would be the entropy at 4. But we have said that this is an isenthalpic process. This expansion is isenthalpic, and the enthalpy is not changing. So whatever is the enthalpy at 3 would be the enthalpy at 4. So whatever is the enthalpy at 3 would be the enthalpy at 4, and it is 99.56. Now, what is the state? So the state is a liquid vapor mixture. Now we want to know that what is the dryness fraction of this particular point, that how much dry this is. Now you can see it is more close towards the liquid saturated liquid line, the saturation liquid line. So most probably it would have 30 to 40% of the dryness fraction, because it is not close to the saturated vapor line, it is close to the saturated liquid line. Now how we are going to find out this? So it is very important to know. We are going to find out the entropy at 4. So the entropy at 4 would be S4 is equal to SF plus X4 SFG. So this is the formula. You know that when it comes to a dryness fraction, we don't know S4, we don't know X4. So we neither know S4, we neither know nor X4. We want to find out X4. So since we know the enthalpy, so we can find it out from the enthalpy, and enthalpy is H4 is equal to HF plus X4 HFG. Now in this particular formula, we can find out X4 because we know H4. We can find out HF from the table and HFG from the table, and then put it in over here. So what it would become like? So it would be like X4 is equal to H4 minus HF divided by HFG. So X4 would be H4 minus HF divided by HFG, and we know that H4 is 99.56 right over here. 99.56 is H4. So 99.56 minus what is HF at this particular state? Okay ji. So HF at minus 20 degree centigrade. So HF at minus 20 degree centigrade would be 24.26 divided by HFG, and HFG is basically 211.05, and from this you will get approximate value of nearly 0.357. It is 0.357. So this is how you would find X4. Now you have found out X4. So now put it in the formula where S4 is equal to SF plus X4 SFG. Now S4 is equal to SF So what is the and the SF is 0.0996 plus X4 is 0.357 and SFG is actually SFG would be equal to, let me find it out on a calculator. The SFG would be equal to it is basically 0.8336 is 0.8336. So SFG is basically SG minus SF. So it will come out to be approximately, let me calculate it, it is 0.0996 plus 0.357 into 0.8336, and it comes out to be 0.3972 kilojoule per kilogram Kelvin. So we now know S4. So we are going to put it right over here, and that is 0.3972. 0.3972 is S4. Now we can also calculate the pressure over T4. So what is the pressure at T4? So what is the pressure at T4? What is the pressure at T1 would be the pressure at T4. Since over here at P1 the pressure is 132, so it would be 132.9 kilopascal. Now this table has been completed, and now we can actually find out the COPs, the for Carnot cycle, for a reverse Carnot cycle, for the vapor compression cycle, ideal vapor compression cycle, and actually we can also find out the tons in refrigeration as well. So we have completed the table, and this completion of the table means that you have actually solved the problem. Now it is very simple. You just have to take the values from this table and put it in the respective formulas, and you will get the answers. How? Let us solve. We have been required to find out the COP of the refrigeration. So COP of the refrigeration, and for that we know that the formula is Q absorbed divided by work input. So that is the COP of refrigeration. Now what is QA? So QA is the heat absorbed, and that is actually where the heat is absorbed. You can see that the heat is absorbed right over here from 4 to 1. So from 4 to 1, so it would be M dot H1 minus H4. So H1 minus H4 divided by work input. Now where is work input? The work input is into the compressor from 1 to 2. From 1 to 2 is the work input, and that is M dot H2 minus H1. Now M cancels out, and COP of the refrigeration is H1 minus H4. Now what is H1? This is H1 minus H4. This is the H4 value, 99.56. So it is 235.31 minus 99.56 divided by H2. H2 is 275.1 minus again H1 is 99.56, and you will get the approximate value of 3.41. 3.41. So this was the COP of refrigeration. So you can see that how easy it is to take the values from this table and then put it in the particular formula, because you know all the H values, all the S values, whatever you want, whatever you need, just take it from the table and solve the problem. Now another thing was required was COP refrigeration of Carnot, and for Carnot we know that the formula is TL divided by TH minus TL, and TL is basically equal to lower temperature. It is minus 20 plus 273, because we have to convert it into Kelvin, divided by Since the change remains the same, so it is of no importance, and that is 44.7 minus 20. So it would come out to be approximately 3.91. Now how this takes place, you can see over here that it is the lower temperature reservoir, which is -2. This is T1 and the temperature is -20. Over here the highest temperature, the maximum temperature, the temperature is basically 44.7 degrees Celsius. 44.7 degrees Celsius. So 44.7 is the maximum temperature minus the lower temperature, and this is converted because it is not a change, and we know that what is ever in a is change is always same in Kelvin as well as in the I would say the degree Celsius. But since this is alone, this is not a change, so we have to introduce the 273 addition of the 273 to convert it into Kelvin. Now lastly, they have asked us about the tonnage of the refrigeration. So obviously the tonnage of the refrigeration is that how much heat it is actually absorbing, and we already know that Q absorb is equal to m dot H1 minus H4, and m is 3 kilogram per minute. H was actually 235.31 minus 99.56, and its unit is kilojoule per Kelvin. Now we have to find out, and we know that when the 1 ton refrigeration is actually, so you have to multiply it, 1 ton refrigeration is 211 kilojoule per minute. So after solving this, you will see that the tonnage comes out to be nearly 1.93 ton. When you solve this, m is the mass, and we know that the mass of 3 kg, and we know that for a 1 ton refrigeration, the energy required is 211 kilojoule per minute. So you have to multiply it with 1 ton, and you can see that all these can cancel out. As you can see that kilojoule cancels out with kilojoule, kilogram cancels out with kilogram, and minute cancels out with minute, and you are left with the tonnage, so 1.93. I hope that you have understand the process. You will actually required to solve it by your own self, and then you have to generate the table. Once you are able to generate this particular table which we were discussing in this particular problem, this table, so it means that you have learned the process, and now you are able to perform the analysis or the calculations of this particular problem. I hope that you have understand the concepts. Do it by your own self, and I am going to give you an assignment on that as well. So stay tuned, and if you have any kind of questions, ask me. Stay safe, stay at home, and you can ask me questions anytime. You can mail me. You can actually ask me questions in the Google Classroom as well. Thank you so much. Khuda Hafiz.